Thank you so much for joining us today. We have a very special guest speaker with us today. We have Adil Salim, who is a senior researcher at Microsoft Research. Today, he will be presenting one of the important works in natural language, which is textbooks are all you need. And it focuses on the surprising power of small language models. So, thank you so much for joining us today, Adil, and over to you.
Thank you. So thanks a lot thanks a lot for the invitation. Yeah, I didn't know what Cohere for AI is. I still don't know actually. I still don't understand what this community is doing, but apparently they are organizing workshops. So this is great. So yes, I'm Adil Salim. I work at. I was at Microsoft Research. Now I'm in Microsoft Gen AI, which is the generative AI unit of Microsoft. And yeah, so this is my first talk on language models. So surprisingly, I'm a theoretician, so I shifted to language models just last year. So it's pretty new for me. So it's the first time I give a talk on language models, and this is a joint work with my group, which was my group in Microsoft Research and also my group in Microsoft Gen AI. So a bunch of people here. And I want to say special thanks to Mojan, who is a co-author, one of my co-authors, for making the slides, because she gave a nice presentation at Microsoft last time, and I told her, I give a presentation on Phi1, you have to give me your slides, and she accepted. So thank you, Mojan, for the slides. So we are going to talk about small language models, and their surprising power. So I'm sure you've seen this graph. Over the past years, we have seen language models of increasing sizes and with capabilities and increasing capabilities at the same time as the size increases. And the common wisdom behind the performance of language models is the common wisdom is that there are two key elements behind the performance of the language models, which are first the transformer architecture, which was introduced in 2018. Here, you should see my mouse, right? You see the mouse? Okay. Anyways, so first, the introduction of the transformer architecture. So the concept of attention in the architecture. So this is the first key element for the success of language models. And the second thing is the scale, right? So the second thing is that as you scale up, the common wisdom tells us that as you scale up, the language model gain more capabilities. So provided you use attention and provided that you use the transformer architecture, the only way to get more capabilities for your language models is to scale up. At least this is the common wisdom, and this is the assumption that we are going to discuss. Okay, but first let's look at the power of large language models. So this is Mojan playing with ChatGPT-4. So you can ask many things to large language models. You can ask to play tic-tac-toe. You can ask to write a proof of math theorems that forms a poem. You can ask to draw a unicorn in Tixi. So this is an example from our group. So yes, large language models can make you more productive in your daily your daily work and what you do. What you do on your laptop, whatever you do on your laptop. It also comes with a number of safety issues, of course, which should be addressed by the community. But what we are going to look at here is the power of the small language models, right? So this was ChatGPT-4. So GPT-4 is a huge model, and but we are going to look at the power of small language models. And we are going to ask whether these emergent capabilities can be achieved at smaller scale. And this is the line of work of our group, the Phi team. We want to answer this question, and we want in particular to achieve performances with small language models, so SLM, small language models, which are comparable to models of higher scale. Okay, so the paper that I will talk about is textbooks are all you need. So in this paper, we introduced our first model, I mean, the first model of our team, the Phi team. So it's called Phi1. It's a 1.3 billion model, and it's specific for coding with Python. Okay, it's a specific, very specific language model, but its performance is comparable to models which are 10x larger and 100x, 10 times more parameters, okay, in the architecture, and 100 times more data, okay? So as I said, this was a specific model, but can we obtain like a general model with performance which are comparable to models of higher scale? And the answer is yes. So after Phi1, we introduced Phi 1.5, Phi 1.5, which is a natural language model, which is also comparable to models which are larger, okay, while being smaller, okay, comparable for natural language performances. And finally, last fall, I guess, yes, last fall, we introduced Phi 2. So it's a 2.7 billion model. And let's look quickly at the performance of Phi 2. So this is for common reasoning. So on the left side is common reasoning, and the right side is language understanding. So for common reasoning, we compare Phi 2 to some other competitors, Llama and Mistral, essentially, on some benchmarks. Okay, so the benchmarks for common reasoning are, benchmarks that will evaluate your ability to perform some reasoning, of course, and benchmarks for language understanding there are benchmarks that are here to see if you are able to to point out to an information in a text or things like that. Okay. So the bar plots here represent the performance on benchmarks. And we see that for common sense reasoning and language understanding, Phi 2 is comparable basically to Llama 2 70 billion. Okay, so a model that is much larger than Phi 2. Okay. For math and coding, we also evaluated Phi 2 on some benchmarks, so some common benchmarks, GSM 8K, HumanEval. So we are going to talk a lot about HumanEval. So it's a benchmark that evaluates your ability to write code. Okay, and once again we see that Phi 2 is comparable to models which are larger, such that Llama 2. And finally, we evaluated Phi 2 on Big Bench, which is a corpus of benchmarks. And once again, Phi 2 is comparable to Mistral 7 billion, which is also larger. So, maybe I should say one word about Gemini. So Gemini are the models released by Google. So maybe we can look at the performance of Phi 2 on a single question that was when Google released their most capable model. It's called Gemini Ultra. They used that example as part of the presentation. So you have a skier that slides down a frictionless slope of height 40 meters and length 80 meters. And the question is to compute the speed of the skier at the bottom. Okay, so this is this was the presentation of Google when they released Gemini Ultra, and of course Gemini Ultra answered the question correctly. But we asked the same question to Phi 2 to see what will be the answer of Phi 2, and this is the answer. So I give you like 30 seconds to read the answer. So you see, like, I mean, I really like this answer. I mean, I like physics, so I like this answer because it uses like conservation of energy and how, the global energy is conserved, and it's conserved, but potential energy at the beginning is transformed into kinetic energy at the end, and yeah, I the answer is correct, but on top of that, I really like the reasoning. The reasoning on energy that is transformed from potential to kinetic energy in order to find the speed at the end of the slope. Yes. So yeah. Okay. Then they had like a follow-up question for which.
It's correct,
yeah.
right?
What?
This particular answer is correct, right? I mean,
Yeah, yeah.
yeah. Okay. Thanks.
Yeah, it's correct. Yeah. But I was saying, so on top of being correct, I like the reasoning on top of being correct. This is my personal, personal, opinion on this answer. But yeah, it's correct. And Gemini Ultra was correct as well. And then, so in their presentation, I think Google like asked a follow-up question to Gemini Ultra, and Gemini Ultra answered correctly, and Phi 2 again is able to answer correctly. We don't have to spend more time on it. So this was just to showcase Phi 2. But what we are going to talk about is we are going to talk about Phi 1, because the root, the root of Phi 2 is of course Phi 1. And in particular, what is the secret sauce to make like small language model, to make small language model, to have small language models whose performance are comparable to larger models. So we are going to talk about textbooks are all you need, and maybe the punchline for this paper. So textbooks are all you need is the paper where we presented Phi 1. Okay, but the main thing is, like, if you want a good small language model, is to have high quality data, high quality training data. Okay, so that's the main thing. So if you want to remember only one thing for this talk, is that small language models are achievable provided that you have high quality data. And having high quality data is a lot of work, right? It's a lot of work. It's a lot of you have to evaluate the data manually. You have to open, like, really, like, click on the data set, open the data set, read like 100,000 lines of the data set to understand what are the problems, what is good, what is bad, what you have to filter out. It's a lot of work. That's why, even when I gave you this example, I gave you 30 seconds to read the question and the answer of Phi 2, because this is really what we do in our daily work. In my group, we spend a lot of time evaluating, like eyeballing the models and the data set. So the questions and the answers, we spend a lot of time doing that. And yeah, so yeah, that was just a parenthesis. So it's really important to look at the data set, and to instead of loading everything in your model, it's really important to spend time looking at the data set and to look at the quality. At least it's really important for small language models. Okay, so yeah, so Phi 1 is a model that is specified for coding with Python. Okay, so if you want to train a model for coding, you will likely look at the stack. So the stack is a big data set of code, which is basically every source code that is in GitHub. Okay, it's 1 trillion tokens. But if you look at the data set, okay, so you open the data set, and you look at a random sample from the stack, you will see something like that. Okay, so my question for you is: do you think that we can teach algorithmic to a human by presenting script like that?
Maybe yes. If somebody actually tried to find the pattern, but in a very longer sense, no, because it would be daunting to read all the code lines.
Yeah, so this one is about, this one is defining variables. So most of the samples from the stack, they are like that. Actually, they are like that. They they are not like that, but most of them, it's very difficult to teach algorithmic to human with it. Okay, because it's something like that contains only variables, or code that is not commented, or many problems that there are many problems that will make difficult teaching algorithmic to a human. And of course, if it's difficult to teach algorithmic to a human, it's going to be difficult to teach algorithmic to a model as well, right? So my point is that a big part of the stack is actually useless to teach algorithmic. So our idea is the following: if we have a small data set that is focused on textbook quality educational content, then we should be able to learn the task better, even with a smaller model. So we are going to look at the stack and to select in the stack the best samples from the stack and use that in our model. And this way we should be able to have a smaller training set. And with a smaller training set, we should be able to train a smaller model to achieve comparable performance. So you see, it's a simple idea, right? It's a simple idea. Okay, but how do we build this high quality data set? Okay, so the first thing that we did is to filter web data. Okay, so when you have web data, you can use GPT-4 to classify the documents based on their educational value, right? So these are two examples from. So here you can see two examples from the stack. So the left one would be an example with high educational value. So if you look at this example, you see it imports PyTorch. It defines some normalization functions for vectors, some Euclidean distance function, some cosine distance function. Okay, so this on the left side, it contains some algorithmic, right? But once again, on the right side, this is what we would label as low educational value because it does not contain algorithmic. It's only variable definitions. So GPT-4 is able to classify. If you give a bunch of documents, bunch of Python script, GPT-4 is able to classify the data set as high educational value or low educational value. But the challenge is that it's expensive. It's expensive because, like, if you look only at Python code in the stack, it's going to be 26 billion tokens. So if you use GPT-4 to classify 26 billion tokens, it's going to be very expensive, right? Because each time you prompt GPT-4, you pay, right? You pay a small amount, but you pay. So if you do that a lot, you're going to pay a lot. Maybe, I don't know, millions or thousands, whatever. But it's going to be expensive. So you need to find another idea. So what we did instead was to so we did the following. We took a small subset of the stack Python, okay, and we label it manually. So it was like 1,000 script. So we were 5. On this task we were 5. So it was like maybe 200 each. So we looked at the 200 Python script and we labeled them as a high educational value or low educational value. We gave a grade, if I remember correctly. So you see, it's a lot of manual work. I told you it's a lot of manual work. So I really opened 200 elements of the stack and gave grades. And I remember I was traveling at that time, so I was busy doing something else, but I had to do this work for the project. So then with this 1,000 script label, we extended the classification using GPT-4. Okay, so we use GPT-4 to classify 100K samples. Okay, so we teach GPT-4 how we want to label, and then we want GPT-4 to replicate the classification on 100K samples, which is much cheaper than using GPT-4 for the 26 billion tokens. And then so based on that, we have a data set of samples from the stack, which are labeled, right? 100K with 100K samples, right, which are labeled. And from this we derive like a supervised learning problem. The supervised learning problem is to classify the data set, and on the training set we have the classification that is written by GPT-4. But at the end of the day, it's just a classification. It's just a classification task. So then to extend the classification to the whole 26 billion tokens, the whole stack Python, we train a random forest classifier, and this is very cheap, right? So we trained a random forest classifier and extended the classification to the rest of the Python stack, right? So yeah. So this is what we did, and this way we obtained 6 billion tokens of high quality high educational value samples. Okay, 6 billion tokens. So this is our first data set. Now, second thing that we did is to create synthetic data. So synthetic data is first synthetic textbooks. So we want to teach the model coding with natural language. So we want, to write a textbook on natural language. Sorry, a textbook on coding, but in natural language, and so that we can put that in our training set. But the challenge when you do that is that it's difficult to obtain high diversity in the textbooks, right? Because if you ask like GPT to write 10 textbooks on I don't know, undergrad computer science, the 10 textbooks might be different, but they will really look alike. Okay, so the challenge is to obtain high diversity and low repetition in the textbooks. So we want diversity in the coding concepts, in the skills, in the level of difficulty, etc., etc. So how did we address that? So to address that, we inject creative randomness in the prompt. So when we prompt, so we use GPT 3.5 for that. So when we prompt GPT 3.5 to write a textbook on some computer science topic, we try to be creative in the prompt, and to introduce randomness in the prompt such that the textbook that will be written by GPT 3.5 will be diverse. Okay, and this is an idea actually that we borrowed from a past work from two members of our group, Ronan Aldan and Manjuli, on tiny stories. So in this work, what they did, they needed to create a data set, a diverse data set of short stories in English. And to do that, they first created a large vocabulary of words, which could be words that you could see in short stories. Okay, so they created this vocabulary. Of course, the vocabulary was created by GPT-4, GPT-4, I think. And then to create the stories, they asked the model to they randomly sample words from the vocabulary, and they asked the model to write a story, including the words that they sampled from that they sampled. Okay, and this way, the model is forced to be diverse because it has to include the words that were sampled from the vocabulary from the dictionary. Sorry, I was saying vocabulary. I wanted to say dictionary. So this is one way this is one technique you can use to be diverse in the prompt. So you see, it's also a lot, like this project is also a lot of prompt engineering. So this way we obtain 1 billion tokens generated by GPT 3.5, and the 1 billion tokens are textbooks, which are diverse because we were diverse in the prompting. Okay, so these two things, they constitute our pre-training data set. And I will show you the performance of a model that is trained on this pre-training data set. Okay, so I will show you the performance of the model that is trained on this pre-training data set on a benchmark called HumanEval. So HumanEval is a benchmark that evaluates your ability to complete code. Okay, so this is on the right side here. This is an example from HumanEval. So you need to write a function that is prime n, and this function has to return true if the number n is prime and false otherwise. Okay, so this is an example from HumanEval, and you have to. So the task of the model is to write down the function. Okay, so this is what HumanEval looks like. So I want to show you the performance of a model of models that are trained from the stack without filtering, and models that are trained on the stack with filtering. With filtering and synthetic data set. So our pre-training data set. So if you take a 350 million model that is trained on the stack, so it is such that it sees during the training 26 billion tokens, then the performance on HumanEval will be 11%. If you train longer, such that the model sees 76B tokens in the training, it will reach 12%. And if you train a larger model, 1.3 billion, and such that it sees 60B tokens, it will reach 17%, right? So this is when your data set is just the stack, unfiltered web data, just the stack. Now, if you use our data set that we created by, once again, filtering the stack and creating synthetic textbooks. So the combination of the two is our pre-training data set that we call code textbook, okay? And you do the same exercise, okay? Then the 350 million model with 26 billion tokens seen will reach 16%. The other one, that is the 350 million model, 350 million parameters model that is trained longer will reach 20%. And the 1.3 billion model will reach 29%. Okay, and this model that reaches 29% it's a model that we'll call Phi1 base. Okay, because it's going to be the base for Phi1. So yeah, so this is just to show the importance of having good quality training pre-training data. Okay, so we obtained 29% with Phi1 base, but now this was only for pre-training, and now for fine-tuning, because we want to train a model that is able to complete Python code. For fine-tuning, we created a data set of called code exercises to align the model to perform function completion tasks based on natural language instructions. Okay, and this code exercises, it was generated by GPT 3.5 once again, and there is less than 1 million exercises, so roughly a bit less than 200K tokens. And yeah, the challenge is the same as before. When you generate with GPT 3.5, you have to address the problem that the diversity problem, the problem that all exercises will likely look the same if you are not creative in the prompt. So once again, there's a lot of prompt engineering and how you make sure that the data set code exercise will be diverse. Yeah, so this is just a random example from the dataset code exercise. So you see you have like the function, the name of the function, then you have a doc string that explains what the function does, and then you have the function. Okay, so this is our fine-tuning dataset code exercises, which was also generated by GPT 3.5. And now, if we fine-tune the models that I presented before on code exercises, we see a boost in performance on HumanEval. So you see the small model, 350 million, that was trained like only for to see 26B tokens, reach 41%. The other one, 350 million, that was trained a bit longer, 76 billion tokens, will reach 45%. Okay, and we call it Phi1 small, this one. And the Phi1 base that is fine-tuned on code exercises gives you Phi1, which reaches 51% on HumanEval. Okay, so once again, it's code textbook, which contains filtered stack and textbooks for the pre-training, and for the fine-tuning, it's code exercises, which contains exercises to train the model to perform Python completion. Okay, and this is our model Phi1, which is 51% on HumanEval. Now, if you want to compare Phi1 to other models, basically the punchline is that if you look at the models that are less than 10 billion parameters in size, then the previous best was 30%. Okay, and Phi1 is only 1.3 billion, and it reaches more than 50% on HumanEval. Okay, so that's it. So the conclusion is that with small language model, you can achieve. So small language models are small language like good performance with small language model is achievable with generation and utilization of data with textbook quality in contrast to conventional web data. Okay, so yeah, so thanks for listening. I'm Adil Salim. So Adil SLM on Twitter. SLM is for Salim, not for small language models. And this is my address email. I mean, my email address if you want to send a message. Oh, what happened?
We have a few questions. So
Yes, yes.
yeah, please unmute yourself and then you can ask.
Yeah. Hi, Adil. Thank you so much for a great
Hi,
presentation.
thank you.
Uh, I have a question, follow-up question. So when you said textbooks are all you need and we are learning from the high educational value data for our small language model. So what do you think the viability, let's say I have a course in the university which I'm taking over the semester. Can I make a customized model with all of the slides or the reference textbooks that are suggested or strongly advised for, like, let's say 6 classes, and I can actually put them in a model and I can get my customized DA?
Yeah, so yes, so this is what we mean by textbook quality. So it's typically like university courses and things like that. So the thing is that so there are two problems. The first problem is that you need a lot of textbooks, right? Yeah, you need like 1 billion tokens, so it's a lot of textbooks. So if you take a course over the summer and you use that for your model, it's gonna be it's likely to be too small. Like you would need several of them. And the second thing is that if the second thing, which applies for me, but maybe not for you, is that I work for a company and we have rules, so we cannot use textbooks without being allowed to, right? Because many content is under copyright, so we can use like open textbooks, like there are some textbooks which are available online and they are free to use, but most textbooks that are from university or from any libraries, they're under copyright, so we are not able to use them in our model, right?
Right. So like when you said a lot of textbooks are needed, can you give like some kind of idea? So I'm kind of like trying to gauge an idea. What does it mean to have like 2 billion? Like how many textbooks?
Oh, how many textbooks? It's a good question. I don't know. If you say a textbook is 100 page, and on each page there is how many tokens per page? Maybe if you say 10 tokens per line, and 1,000 tokens per page, maybe. So 1,000 tokens per page. So that's 1,000. So 100,000 tokens per textbook. So this means you see, like if you want
How-
like what so if you want one, yeah. I mean, you see, you need like 10K textbooks or something like that, right?
Okay. Okay. Yeah. So yeah, definitely it was helpful. After the legal considerations and all and everything, I think that might be really nice to have an individual TA for you for your semesters.
To have what? Sorry.
To have an individual teaching assistant for you, because it would be, the model would be trained on all of your courses and materials and stuff like that. So instead of interacting with the TA, you can actually interact with the model to discuss your doubts, confusions, and queries.
Yeah, I think this is something that would have a huge impact on education if we were able to have like you know a TA. It's really something. It's actually something I'm interested in, but it's it's difficult because the TA should be able to. Maybe the most challenging task for that is that the TA should be able to fix your mistakes, and
Right.
fixing mistakes with models it's I've spent time doing that. It's difficult, but yeah, hopefully like in 2 3 years we should be able to have something like that. And I think this is one of the one of the domains where language models can have a huge impact, in my opinion. Yeah.
So can't we actually try to better our fix mistakes with RLHF?
Uh, yeah, I mean, I don't know. I don't know. RLHF, yeah, I mean, probably, probably. I don't know. I'm just saying that it's a challenging task. So what is challenging is to have a data set where you know, yeah, probably RLHF, yeah. Because what is challenging is to have a data set where there are mistakes and where the mistakes are fixed, right? Because if you ask, for example, if you ask, I don't know, if you ask GPT-4 to create such data sets where there are mistakes and the mistakes are fixed, usually you get some nonsense. So maybe RLHF is a solution. If we have a lot of RLHF, maybe yes. Yeah.
Okay, thank you so much. That was really helpful.
Yeah.
Hey, thank you for the presentation. And I have a quick question with regards to filtering of existing code data sets that you used.
Yeah.
You mentioned that you did manual labeling and then prompted GPT-4 for additional labeling. So what exactly did you do there? I mean, why would you prompt? Why would you manually label and so on?
Because you want you want to teach GPT-4 to label the way you label. So it's like teachers. Some teachers are very harsh in when they grade, and some teachers are kind, right? And you want to you want the labeling of the training of the first samples to be uniform. So just give some examples to GPT-4 such that it knows how you want the grade to be. How you want the grading to be.
Right.
Does it make sense?
It does. So you basically use that for few-shot prompting as an example?
Yeah.
Okay, thank you.
Yeah. Hi, Adil. Thank you so much for the insightful webinar. I was interested in the, you were mentioning textbook quality data set, and what is your criteria, or what was your team's criteria in determining or in labeling which data set was high quality? And did you do any more layered classification when going through the different data points, let's say, when I'd say curated the data set?
Yeah, so there are two things. So for the classification, okay, so what was your first question again?
Yeah, how were you able to determine, or what was your criteria in labeling what is high quality?
So when filtering, the stack, the criteria was basically when I was labeling, at least I can tell you my criteria was basically would I use this to teach algorithmic to somebody. So if you look at these two examples, definitely on the right, the left side would be if I wanted to teach algorithmic to somebody, I would definitely use the left side rather than the right side, right? Algorithmic, I'm talking about algorithmic, right? Because so this is basically the criteria, the criterion, and then usually most of the samples of the stack, Python, they are these are extreme examples, but most of the examples are in between, right? So sometimes I don't know. Sometimes there is some algorithmic, but there's no comments, for example. Or sometimes, there's some algorithmic, but, there are some mistakes, for example, in the code. So most of it is like in between. That's why we graded, like, I don't remember, from 1 to 10 or something like that. So, but yeah, the grading is not perfect, right? It's not perfect because, first of all, there were several people grading. So we all grade, like we all have different, ways of evaluating things. So the grading is not perfect, but yeah, hopefully thankfully the classifier did a decent job in classifying the good and the bad. Okay. And your second question was?
I actually want to change my second question because your first question, your first answer was super interesting. You guys are like, I remember you mentioned like 5 of you were doing the labeling, and clearly you're all experts in coding and determining what is a good high quality data point. My question is, did you guys use any something like maybe a consensus system wherein all of you look at the same type of data and then
we did something like that. Yes. Yeah, we did something like that. So we had a meeting and how we grade. So we had some rules, like we wrote some guidelines to to be as uniform as possible, but as uniform as possible. So this is what it means. Like you cannot be perfectly uniform, but yeah, we had some guidelines. We looked at some examples to make sure that the grading is not very different.
Okay, thank you so much.
No problem.
So there are a few questions in chat. So the first question is, how good was the random forest classifier compared to the classification made by GPT-4?
That's a good question. I don't know. I don't remember. I don't know. But what I can tell you is that the classification was good enough for our purpose. That because you see, like it's random forest, but it's random forest on the embedding. So you take the sorry, you take the okay. Maybe I should fix that. So it's random forest, but it's random forest on the embedding. So we used an existing embedding of text, okay, into into vector, and we classified the embeddings. So the embeddings contains already some, it contains some understanding of the text, etc., etc. So it was I don't remember that we seen like a big discrepancy between the two classifications. We probably lost a bit using random forest versus GPT-4. Of course, we lost a bit, but it was not striking.
Right. And the second question is, are the datasets public?
I guess no. I mean, at the time we released the model, the answer was no. And I mean, you can check on Hugging Face. I guess no. I mean, some of it is proper. Some of it is okay. What is for sure is that some of it is not publicly available. Now, what I don't know is whether some of it is available, but for sure, a part of it is not available.
Right, good. And there's another question. So how long did it take to create the data set? How long did it take to manually label the data set?
Oh, it was very short. It's it's 200 files per I mean, for this task, there are several things, right? There are the textbooks. I mean, this project, there are several things. So the thing, okay, maybe before answering, I should tell you something. This is very important. This project with several people, it's very new for all of us because we used to work alone, basically. We are, most of us are, doing research in machine learning. So for this project, we had to organize the team in work streams. And some people were owning training, some people were owning data sets, some people were owning other aspects of the project. And I'm talking a lot about data set because this is what I worked on. But some other people who would present Phi 1, they will talk more about maybe training because there's some innovation in the training as well, which I did not mention in this talk. Now, let me, sorry, it's popping up. I don't know how to stop that. Now to answer the question, how much time it took? Well, the manual classification was 1,000 files. We were 5, so 200 each, and it took like 1 week, but not 1 full week. It was the week of iClair, I remember. So I was traveling to Rwanda for iClair 2023, and in my evenings I was doing this labelization work. So it took like 1 or 2 weeks. But not full time, right? 200 200 examples is, is doable. You just need, the only thing that you need is to discipline, right? You just need discipline. You just need to do it because it's boring, right? But it's doable. 200 examples per person.
Yeah, makes sense.
We like manual things. We like, as I told you, we like manual things, looking at the data set manually, evaluating data set, evaluating models manually as well. Before looking at benchmarks, when we have a model, we play a lot with the model. We are manual people.
Even though this clearly works, it's essentially like trying to distill some knowledge out of GPT-4 or yeah, right. But there is also like this talk about no free lunch thing, and that models go mad when you try to get one model to only train it on the data set from created from the outputs of another model. So like training becomes unstable and model go mad. There was a paper on that. So what's happening there? And what's the difference between these two papers?
Can you be more specific? So what can be weird? You said so it can go mad. So can you be more specific, because I don't know what you're talking about.
Um,
Do you have an example, maybe?
Apparently, when you only train some like diffusion models created from the images of other diffusion models, it, it doesn't work very well.
Okay.
So to some extent, it works too good, and then after some point, then it becomes like they start degrading.
Yeah. Okay, I should mute that. Yeah, I mean, we didn't see that. We didn't see that. The content that is written by GPT-4 is or any GPT 3.5 is different, and when we trained on it, we didn't see this phenomenon. Maybe there's some regime where we could have seen it. I don't know, but it's definitely not something that we've seen. Maybe also because we make sure the data set is diverse. I don't know. And also, diffusion models. I mean, if you are talking about diffusion models for images, images are weird, right? Images, classifying images is a task that is very sensitive. Like, if like you take an image, you add a perturbation that cannot be seen by a human, and after perturbing the image is misclassified, right? So images are different. They are very sensitive. So maybe images that are produced by diffusion models, they look like real images, but maybe for algorithms they do not look alike. You see, because there are some invisible things that human cannot see, but the algorithms can see. And I don't think there's this phenomenon for text. Yeah, at least we did not observe this problem.
Yeah, thank you for answering and the talk.
There is another question in chat. So, how did you guys create randomness in the prompt?
Yes, so randomness in the prompt is so you can be random in the topics that is covered. You can be random for the topics that is covered in the level of difficulty. You can be random in what else? At least for textbooks, I think this is the two main randomness. So if you have like 5 levels, I don't remember how many levels we used for the textbook, but if you have like 5 level of difficulty and hundreds of coding concept, it's already 5 times hundreds, so it's already 500 prompts. So. And then each prompt leads to a textbook. So you see the kind of calculation that you can do. So the complexity is increasing with the number of levels that you want, right? So you see, if I want to write a textbook on undergrad math, for example, one thing I can do is to take you take the syllabus of undergrad math, okay, and for each element in the syllabus, you can ask. I don't know. You can ask for each element of the syllabus. You can ask for keywords that would be in the syllabus, for example, and then you can ask. I don't know, the model to write a textbook on this element of the syllabus, but containing, a random sample of the keywords. And this way you have a textbook. You see how it means, like how it works. Like you can add complexity to the prompt using techniques like that.
Yeah, makes sense. Thank you. If we don't have any other question, I think we can end the session here. Thank you so much, Adil, for your time. It was really
Thank
good.
you. Yeah, see you. Thanks for the invitation. It was great to talk about language models. All right.
Yeah, see you.
See
Take
you.
care, everyone.